Hello, everybody. So we, in the atrium, you saw the year 1 students presenting their projects. We're the Northwest Advanced Programming Workshop year 2 students, and we were working on building software for an autonomous car this year. So there are two main tasks when you're building a self-driving car. One is steer the car on the road, and the other one is not hit things that are in the road. Our half of the project was not hitting things, or at least detecting pedestrians. So first, here's a sample of what our program does. It's pretty self-explanatory. Draws a box around the person. You can see in the background there's a little bit of flickering. That's a problem with our program, and it happens a lot because of all the cars and all the stuff like that. And I'll talk about that later. But for now, all you need to know is that the point of this program is to detect where the people are. So how does this program work? There's 5 main steps. The first one is posterizing the image. What that basically means is simplifying the image. On the left, you can see a regular image, and that person's shirt there, to us, it looks like it's blue. And it is blue, but to the computer, there's like 75 different shades of blue in that blue. And so we want to make it easier for the computer to tell what's blue and what's not blue. So we simplify the image into one of 6 colors. Every pixel is one of 6 colors. So it can be black, like the road, gray, like the sidewalk, white, like that stripe down on the bottom, green, red, or blue. And this helps the computer detect where the blobs of color are in the image. And that's really important in the next step, detecting the blobs of color. So the premise for this project was that pedestrians are normally made up of blobs of color, like a shirt might be red, or your shorts might be black. And so we use that information to detect pedestrians. On the left, you can see all the blobs of color that we detected in an image. The pedestrian you can kind of see has a fair number, but the scenery also has a lot too. We did some pre-filtering to filter out most of the scenery so that we only get blobs that are most likely part of a pedestrian. And that's what you see on the right. After we detect the blobs of color, we have to track them over time. Another big part of our program is using the velocity of a blob in order to predict whether it's a pedestrian or not. So these are just hand-drawn boxes, but you'll get the idea. Let's say these boxes move that far in one frame of the video. We match those together and say, hey, that guy's shirt in one frame is that same guy's shirt in the next frame. So with that information, we can see how far the blob moved and therefore how fast it's moving. We use that to predict its next position and help us refine our velocity predictions more and more. And all this is used in the 4th step, which is piecing together pedestrians. Pedestrians are not just one blob. Like on the left, you can see there's the face, arm, shirt, legs. It's a lot easier for us to sort out pedestrians versus non-pedestrians if we have the whole pedestrian as one blob. So we do that with 2 main criteria. On the left, if the blobs are close together, they're probably part of the same object. But almost more importantly, if they're moving in a similar direction, they're part of the same object. Let's say a pedestrian is crossing the road. It'll be really easy to tell, hey, those blobs, which correspond to like head, shirt, shorts, they're moving in the same direction. And that thing is about the right size to be a pedestrian. So we'll say it's a pedestrian. Now, this comes together in the last part, which is removing non-pedestrians. So you can see on the left, there's some squares that our program has identified as potential pedestrians. Well, they're just part of the building, so we get rid of them on the right. So we're left with just a pedestrian. We do this with a little bit of machine learning, which to remove the non-pedestrians. Involved in this removing code are a couple thresholds or values that we use to determine whether something's a pedestrian or not. For example, the speed of an object. If something's moving at like 100 miles an hour, it's probably not a pedestrian. Likewise, if it has a funky shape, it's probably not a pedestrian. So we use an algorithm to try to find the best thresholds. Anyway, so now that you have a basic idea of how it works, we have a couple more videos, 2 more, that are more real-life situations. So here, the car is stopped at a place just outside, actually. You can see it detects people pretty well. And then over here, in another location, it detects this man. So this is pretty useful. Like, you wouldn't want to turn right here because there's a person in the way, even though it's a red light. So yeah. Now, future improvements. So one of the big things we face, big challenges we face, I should say, are things that are far away. So on the left, you can see that there's a red box around one person, but there's actually another person. It's kind of hard to see. There's another person like right here. Okay, and the computer cannot detect that person for 2 main reasons. 1, they're really far away, and 2, they're in the shade. So a lot of times things that are far away, they don't look to be moving as fast because they're far away. So our program thinks, oh, they're probably just part of the scenery, and so it doesn't pick them up as pedestrians. Also, they're in the shade. Now, this photo was taken before we implemented some new software to kind of deal with the shade problem, but this is an example. With bad lighting, it could have a big effect on the results. Next, smoothness of traffic. So you may have noticed this in the videos, but the blobs that surround the pedestrians, they jump around a lot, and they move kind of erratically. It'd be a lot easier for a car to steer out of the way if that square was really stable and easy to predict where it was going. Third, car movement compensation. So all of our testing was done either in a car that's standing still or a car that's moving at low speeds, like through a neighborhood. We don't know how it would work on somewhere like a highway. Probably not on in a race car, but on a higher speed, because the surroundings are all moving pretty quickly relative to the car. So in its current state, our program might think that the field is full of pedestrians, which it obviously isn't. And then finally, and this is tying together our program with the other half of the Year 2 students, is using this information to direct a car. Now, detecting pedestrians is really great, but we need to actually use it to do something, like driving a car. So going into next year and the year after that, we want to implement this software in a real car, starting with a remote control car, and then moving up to actually make a self-driving car that could work pretty well. Anyway, now we want to show you a live demonstration of our program, just with some of our team over here walking across.
Okay, so now let's Nicholas, why don't you go ahead and walk across?
There we go. There we go.
And it draws a white box around him because it thinks that there's a pedestrian right there. And it does the same with me. And now there's a couple bugs in this because obviously the white box is flashing around a little bit, but that is something that we will hope to improve in the future years.
Okay, so now we'd like to invite any questions that you guys have about the program.
Do you plan to just keep doing image analysis or add some type of like depth detection or like checking hardware or something to the vehicle?
Well, currently we don't have plans for that, but we could, one thing, we could try multiple cameras, for example, better resolution. That would require more brainstorming, and given the time constraints of this problem, we didn't think about it that much because we decided to focus on a smaller problem that we could solve pretty well. Yeah.
The pedestrians that were in the videos, they had shorts on and a t-shirt. If they had like long pants on, would it still register them as pedestrians?
That would just mean there's less blobs on the pedestrian. If they're wearing the same colored clothes all the way down, like I was in one of the videos, I was wearing completely blue, then it would have just drawn one blob and would have detected pedestrians.
Yeah, right here.
So could they have worn camo then and been invisible? I mean, can you defeat this?
So we haven't tried camo yet, but we did initially have a little bit of a problem with stripes. but basically that was before the blobs were sort of getting unified together. And at this point, after it sort of unifies all the blobs together, even if it misses a few blobs, it still gets the sort of the general shape. So stripes, at least now, they work fine. So
A related question, when you're looking at a technology like this, how do you want to decide if you've got enough different examples? Sometimes the teams that build technology aren't as diverse as the world that uses technology, and we can actually introduce bias accidentally by only using examples from a part of the world. So have you thought about that at all?
Well, one thing we did was we took some test videos as we were trying to test our program. We took some test videos in like the sunny conditions, having sun and shade in the same image, and then in really shady conditions. So yeah, we were trying to get some of that variety, but yeah, I do think we were still liable to.
Ultimately, we knew that at the very beginning of this project, we knew that we couldn't solve everything.
Right.
So as part of, we were like, we're gonna use this camera, we're gonna solve these pedestrians, car's not gonna be moving, and yeah, limiting the scope.
So this is something that we thought about for a bit, and again, it was to reduce the problem scope, to make it a little bit easier to solve. Normally, people don't stand in the middle of the road completely still. And so we decided to assume that, we simplified the problem and decided to base much of our calculations around velocity. So because in most situations, pedestrians will either be crossing the road or moving in some way. So yes, there are some bad cases when there is a pedestrian standing completely still. But that's a perfect example of a problem that we could hope to solve next year and the year after that. Yeah, over there.
Yeah, what size of block can you identify? Could you identify like a small animal running across the street? Or maybe a ball and predict there might be a small child running after the ball?
Well, if you saw in our first example, there's actually a little piece of trash, a little paper bag that blew by it with the wind, and it actually did pick that up. So that's one example where it did pick up something. But it was moving quite quickly, so that helped a little bit.
But like to answer just like the question, like it's the minimum size for a blob is 4 pixels by 4 pixels. So
A lot of times we don't want to pick up things that are too small because then we're just picking up all the scenery as well. How about over there?
My question is that the approach that you chose, how did you come up with the approach, and do you consider like other approaches like deep learning based approach where you're training like a model based on lots of pedestrians that have sort of like gone ahead? How did you kind of come up with this approach as opposed to other approaches?
Yeah, so the basic framework of our approach was first developed by Tom back there, Tom Pittman, and that was kind of the foundation. We didn't choose to do like a kind of deep learning approach because given what this project is, first of all, to maximize how much we can increase our understanding of software and our understanding of coding, doing a machine learning model would require just a lot of research and a lot of things. You can hear about that more in the next presentation. But yeah, I think it was a lot more fun for us because we got to really dive into the nuts and bolts of how the program works because it wasn't a machine learning model.
Additionally, we did, though we stuck to this original framework because we figured it was a very good solution as we started. We did try other methods of like posterization, for example, or unifying the blobs. A lot of what we found is the more complex and the more deep into research we got, the less it worked. So we tried to keep it simple.
Over here.
So where does your program spend all of its time?
Well, many places.
Many places. Most of it, so there's a little bit of time associated with getting the frame off of the camera. There's a little bit of time associated with processing that frame. We get raw frames off the camera as in like just what the sensor has. There's no processing on the camera from that. So we have to process that on the computer, turn it into something our code can understand,
And then we have to posterize it, which is simplifying all the colors. And then after that, we have all the identifying of blobs and the filtering, and I think that's about it. And then after that, we display it. So actually, most of the time is evenly split in between those steps. There's no really one slow step.
So you measured it?
Yes, actually, right before this yesterday.
Yeah, how about over there?
Yeah, what programming languages and development environments did you use, and would you use it again or switch?
So we use Java mostly, and we use many IDEs, interactive development environments. But yeah, we use Java and a little bit of C++. Well, C.
Yeah, we IntelliJ, Eclipse, NetBeans. We really should have standardized. It led to a lot of interesting problems, but yeah.
So yeah, it's about 90% Java, and then there's a little bit of C code involved with getting the frames. So the camera only provides a C API and a Python API, and the Python is just wrapped around the C. So.
And also we believe that Java is good because it's very widely known language compared to more obscure languages.
How about right here in the middle?
How did you manage to meet 6 people working on one project?
That's a good question.
Well, we actually had like, how many people, like 11, 10?
Oh, a lot, yeah.
But there's different complications for why people can't be here today. It was quite difficult actually. After the start, at the very start, we split it up into 5 different tasks, those 5 different tasks that you saw in the presentation. And so then it was just 2 people working on the task, and they didn't really have to worry much about what other people were doing. After we got the program going, people kind of moved around and blended, and it just kind of required a little bit of extra effort when we were merging in Git.
Yeah, over there, red shirt.
So I have 2 questions. First one is, will the final car have access to road data or like map data to know where pedestrians probably should or shouldn't be?
Well, so we don't know what the final result of all this is going to be many years down the line, but what we're hoping to do next year and the year after that is, well, next year at least, is get a small like go-kart type device and train it on like a track of some sort.
All right. And then my second question is, I don't know if you tested it in these conditions, but how do you think different weather conditions like heavy rain or hail or something like that will affect the pedestrian detection?
Well, it'll definitely affect it. We don't know for sure because we didn't test it in those conditions. But yeah, it's been pretty sunny. One thing is like one thing is the shade and the darkness. Like we kind of touched on that a little bit, but it can mess with the program. We added some code to prevent that from happening, but we don't really know until we try it. Yeah, over there.
What about cyclists? There's lots of cyclists on the road.
Yeah, so those, following the procedures of our algorithm, those would probably get picked up. We don't have any test videos with bicyclists biking across the road, but you can imagine they have blobs of color, like shirts, pants. So we don't know for sure, but my guess is they would probably be picked up.
And is there a speed thing? What if somebody's running really fast?
Yeah, so if they're running really fast, it's possible that they might not be detected because they're going too fast, but the maximum velocity is pretty high, so that would rarely, if ever, happen.
The maximum velocity was mostly intended for things that were falsely matched, and so they would move halfway across the screen. So anything that is actually an object moving in the frame will probably
Anything that's moving faster than the maximum velocity at this point is either not going to be hit because they're going so fast, or even if we try to brake, we're going to hit them. We're out.
Did you use any libraries or you wrote all the code yourself?
This was all our own code.
except for the camera.
Except for the camera,
yeah. But
other than that, we didn't use any
Most of the code for the camera, the wrapper anyway, was originally written by Tom, but then eventually we had to get our hands dirty and start poking around in that anyway.
And we sort of immediately did.
Yeah. It works. Tom is motioning us to wrap it up, so is there any last questions? One more.
Yeah.
We do have a self-driving car right now. What's the confidence level you have now after the project? You will willing to be a passenger of that?
Well, right now, since it doesn't actually do anything with the data it gets, I would say 0% confidence. But once we actually implement this software, we'll see.
We're very proud that we solved the problem we set out.
Okay, well now we want to introduce the next group. So.
Alright, hello everyone. My name is Savannah, and we are the second group of second years for the Northwest Advanced Programming Workshop. And our portion of the self-driving car problem was lane keeping and steering, so making sure the car stays on the road where it's supposed to be. And to do that, we used a convolutional neural network.
So, just a bit about why self-driving cars are important. A lot of people die on the road, so there are about 35,000 deaths every year. And if we could have machines that are really good at driving, they aren't tired, they aren't drunk. If we save just a few deaths, that would already be great. And then there are also benefits for stuff like traffic congestion during the transition between having a bunch of self-driving cars and people still driving manually. Like, there's a study that showed that adding 5% of driverless cars would significantly reduce traffic. And then there are also other benefits for people like the elderly or those who are blind, who just don't have a license for whatever reason. It would give them mobility. And then far in the future, when you don't have to pay attention, you could be doing your own thing in the car. And as Savannah said, so the first group focused on obstacle detection, and we're trying to follow the road and get steering angles.
So an overview of neural networks. So a neural network is based kind of loosely on the human brain, where you have certain neurons that work together and basically take in data and do the middle part, the hidden layer, which is what it's called. Do a function, apply it on a function, and then output, in this case, the steering. And so, you have the input layer, which in this case would be an image of the road. The hidden layer is self-magicalness. The output layer, which is the steering.
Alright, so why neural networks? Neural networks are uniquely suited to the task of image recognition because of the way that computer vision works. So if you saw in the last group, computers don't see images as objects like dogs. You as the audience can observe that all of these are dogs. They see it as pixels. So for example, when comparing this image of a dog really close to the camera to one that's super far away, the computer would compare them pixel by pixel and would say, look, none of these pixels match up. These are clearly not the same thing. Additionally, this picture over on the left is the same picture. It's been flipped horizontally and it's been darkened in one of the instances. So again, when those are stacked on top of each other, the pixels don't match up. And additionally, in the way that the computer sees color, it lists the RGB values of each pixel. So for the darkened version, one point would be 73, 48, 27, and the same point on the lighter version will be 198, 135, and 91, which is a pretty significant mathematical difference. So it'll see those as totally different colors, even though we see them as different shades. However, when you use a neural network, you feed it generally hundreds of thousands of examples of something, for example, a dog. And as it looks at each example, it'll find things that each dog has in common. Every dog has ears, eyes, it has a body, it has textured fur. And so it'll be able to recognize a dog, whether it's up close, far away, or whether part of it is obscure, or even if it's a kind of weird looking dog, like a shaved poodle.
So if you have a neural network, if you enter 100,000 images of dogs into a neural network, you could expect the neural network to come up with certain patterns that it's trying to find, in increasing complexity based on each layer of the depth of the neural network. For instance, the first layer, for instance, come up with like, are there circles in the image? Are there triangles? Are there like lines? And then the second layer after that would use that information to come up with more complex patterns like ears or eyes or a nose. And then that information can ultimately be used to answer the last question of the output, like, is this an image of a dog?
Now, what a convolutional neural network has is these things called filters. And to put it simply, these filters basically act sort of like a magnifying glass and looks for different patterns in every image. Now, typically, these convolutional neural networks actually have multiple layers of these filters, so they can look through all those patterns, like as modeled with that last slide with the neural networks. And also by doing this, it also compresses the image to a form that's much easier for the computer to actually process and start learning and training from this.
Alright, so now that you guys have a very high-level overview of the types of techniques we use, I'm going to get a bit more into the specifics of the network that we implemented. So, different neural networks, while anything that has at least one hidden layer can theoretically do anything, depending on your network, like the structure of your network, you can see a structure here, like which layers you have, what size they are, etc. The amount of time it takes to learn your model might vary wildly. And so, when we did some research and we found that this particular paper by NVIDIA is actually sort of kind of a standard paper in this area. Like if you look at a lot of other people that try to do steering angle prediction, they either typically have some network that's either based off of the NVIDIA paper or integrates aspects of the NVIDIA paper into the network. And you can see, right here, their network starts with like an image, and then it goes through several convolutional layers that act as filters, and then at the end you have some normal layers to kind of take the abstract details that the filters have found and kind of turn them into a single steering output.
Alright, so to write our implementation of that paper, we chose to use the Tensorflow library, which was originally written by Google and released for public use in early 2015. So Tensorflow offers a fairly high-level approach to writing the code, and it uses Python to bindings to communicate with a fast C framework with support for CUDA GPU acceleration. So Tensorflow is also a fairly popular library, and as Alec mentioned, there's a lot of community papers that implement the same NVIDIA paper. There's also an official convolutional neural net tutorial that allowed us to have the baseline to start off with.
So with the Udacity simulator, we've got training mode and autonomous mode. So in training mode, in the simulator, you just drive around the car and then you press the record button, and there's left, center, and right cameras on the car, so you get 3 images, and then you also get steering, angle, throttle, brake, and speed data as well. And in autonomous mode, you can connect your neural network and just watch the car drive by itself.
So we also used Euro Truck Simulator 2, both for data collection and as a driving simulator. So using a couple of Python screen capture libraries, virtual controller frameworks, a couple of mods, and well, a steering wheels, we were able to train, validate, and then visually test the success of our network in a fairly realistic environment.
Okay, and for the actual training of the network, we used the 15,000 images and labels from the Udacity challenge and 15,000 more, which were generated by the Euro Truck programs which we made. And training a network takes a very, very long time. So of course we have the training montage up there. But what we had to do was initially get the convolutional neural net tutorial for TensorFlow. Initially only worked on CPUs. So we had to change it to work on GPUs, which can train a neural network about 200 times faster than a CPU can. And then we used Amazon Web Services with cutting-edge GPUs to actually train our neural network.
We'd love to take any questions that you guys have about our process or our current results. Yeah.
So I was wondering whether you guys were thinking about training the neural network to make moral decisions, such as, if you're driving down a road and then all of a sudden a situation comes up where you might accidentally, drive off the road, killing the people in your car, or possibly crashing into another car, which I know wasn't quite part of the data set that you guys are training on, but do you think that this is a good thing for neural networks?
Well, 2 things. The goal that we're currently achieving is just lane keeping. We're not dealing with any obstacle detection right now, so that question is a little bit outside the scope of our current problem. And to deal with the second part of your question, it depends on what system of morals you decide to apply.
Once it stops running over pedestrians willy-nilly, then we can have it decide when it should run over pedestrians.